Hello guys, welcome to my new channel Edu Success 2 Cross. So today we will study about series and parallel combination of resistances, and also we will see the derivation of a power of the series and parallel combinations of the resistances. So let's begin with the session resistances. So let's start. So let's take the circuit. Let us consider there are three resistors that are connected in series in the circuit. This resistance is R1, this resistance is R2, and this is the resistance that is R3. Here voltage is V. So now the voltage that is developed across R1 is VR1, voltage that is developed across R2 is VR2, and voltage that is developed across R3 is VR3. So now this V is the combination of VR1, VR2 and VR3. Now current that is flowing in the circuit is I, because here I current is flowing. So now this V is the combination of VR1 plus VR2 plus VR3. VR1 is the voltage drop across R1 resistance, VR2 is the voltage drop across resistance R2, and VR3 is the voltage drop across resistance R3. So now V is equals to I into R. R is the equivalent resistance of the circuit, and R is the combination of R1, R2 and R3. That is equals to VR1 is the current into resistance R1 plus VR2 is current into resistance R2, and VR3 is current into resistance R3. So from both sides I will be cancelled out. So IR is equals to I into R1 plus R2 plus R3. So now cancel out this I. So we will get R is equals to R1 plus R2 plus R3. So this is the formula for the resistance, equivalent resistance of the series combination. Now we know that I is equals to V by R. I is equals to V by R. So now V upon R is what? R1 plus R2 plus R3. So in this way, when a number of resistances are connected in series, so in this way we will calculate the value of a current. Next, to calculate the power, so P is equals to I square R, we all know. So here three resistances are connected, so we will calculate I square R1 plus I square R2 plus I square R3. Now here we will take out I square common, I square into R1 plus R2 plus R3. So this will give I square into R1 plus R2 plus R3. So we can also write this in the form of voltage. So here it will be VR1 I into VR1 plus VR2 plus VR3. Okay. So this is the formula for calculation of a power in the series combination of a resistance. So now let's take another circuit, and we will prove for the parallel combination of a resistances, the same power and resistance formula. So now parallel combination. So here let's draw the circuit. There's a circuit. Here are three resistances that are connected in parallel. First resistance value is R1, second is R2, third is R3. So here let's take the current that is flowing across R1 is IR1, the current that is flowing across R2 is IR2, and current that is flowing across R3 is IR3. There's a parallel combination of the circuit. Now this is V here, the polarity is plus minus V. Now current that is flowing here is I, and I is equals to IR1, IR2 and IR3. This you will see here that because this I current is dividing in three parts, that is giving us IR1, IR2, IR3. So now here we can see in parallel voltages are same. So V will be equal to voltage across this resistance R1, that is equals to VR1 is equals to voltage across resistance 2 is VR2 and voltage across resistance 3 is VR3. So here VR1 is IR1 into R1, VR2 is IR2 into R2 and VR3 is equals to VR3 is IR3 into R3, that is equals to V. So these all voltages are equal because they are connected in parallel with the voltage source. So now I is equals to, as I have told you all, I is equals to IR1 plus IR2 plus IR3 because this current I is dividing into three parts. So I is equals to IR1 plus IR2 plus IR3. Now substitute the value. I is equals to V upon R, and this IR1 is equals to V upon R1 plus IR2 is equals to V upon R2 plus IR3 is equals to V upon R3. So take out V common from both sides. So V by R is equals to V 1 upon R1 is 1 upon R2 is 1 upon R3. So now 1 upon R is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this is the value of equivalent resistances in a parallel connection circuit. So now suppose if two resistances are connected in parallel. If two resistances are connected in parallel. So here we will get 1 upon R is equals to 1 upon R1 plus 1 upon R2. So that is equals to R is equals to R1 into R2 upon R1 plus R2. So if two resistances are given in an equation, so directly you can, for calculation of equivalent resistance, you can directly put this formula, those values of R1 and R2, then this formula, and you will directly get the value of equivalent resistance. Also, if you want to calculate the value of current, so here we know that I will be equal to IR1 plus IR2 since two branches are there. So current will be divided in two parts, IR1 and IR2. So that will be equal to V into 1 upon R1 plus 1 upon R2. Now this will give V is equals to what? IR1 into R1. Here it will be R1 plus R2 upon R1 R2. IR1 into R1 is taken from the fact that voltage is in parallel, voltage is same across all the branches. So here we can write V as IR1 into R1. So now R1 will be cancelled out. So now I is equals to, or you can calculate from here, IR1 is equals to I into R2 upon R1 plus R2. So this is the current division rule that we will discuss later on, but now we will only see about the parallel combination of resistances. So now let's see next formula for parallel connection, that is power loss. Now let's calculate power loss parallel circuit. That is P will be equal to PR1 plus PR2 plus PR3. So now that will be equal to IR1 square into R1 plus IR2 square into R2 plus IR3 square into R3. Now this will give us B square upon R1 plus B square upon R2 plus B square upon R3. Now take out B square common, so B square into 1 upon R1 plus 1 upon R2 plus 1 upon R3. So that's the formula for the power for parallel combination of circuit. That is equals to V square into 1 upon R1 plus 1 upon R2 plus 1 upon R3 into and units will be watt. So hope you all understood each and every point. So meet in the next session. Thank you. Hope you all liked the video. Please like, share and subscribe. Thanks for watching. Press the bell icon.